Okay, welcome everyone to another video lecture series for analytic geometry. Okay, so today's discussion would be on polar coordinates. Okay, so for our objective for today's topic discussion, we'll have the following: demonstrate the system of coordination in polar coordinate system, and identify the polar equations and graphs of circles, conic sections, leaf rows, graphs, spirals, and limacons. Okay, so let's start with today's discussion with the introduction of the polar coordinate system. Okay, so aside from the Cartesian coordinate system or the rectangular coordinate system, another way of coordinating points on the plane is through what we call the polar coordinate system. Of course, there is a transition between the Cartesian coordinate system or the rectangular coordinate system into the polar coordinate system and vice versa, as we will be introducing later on. Okay, so we shall refer to the coordinates of a point in the Cartesian coordinate system as a rectangular coordinate or Cartesian coordinate, while its coordinates in the polar coordinate system as the polar coordinates. Okay, so we have the rectangular coordinates and the polar coordinates, or the Cartesian coordinates, or uh, the polar coordinate system. Okay, so assignment of polar coordinates, we consider an arbitrary point O on the plane. We call the origin and the ray H from that point. Then we assign 0 and 0 degrees as the polar coordinates of O. Now consider an arbitrary point, which meaning r is not equal to 0. Let p be the distance between O and r, and let theta be the angle between the ray H and line segment OR. Okay, so this is your line segment. Um, this is your ray H, this is your point R. The distance from the origin to point R is P, and the angle that this line segment OR makes with the ray H is angle theta. Then we assign the coordinates P, theta as the polar coordinates of R. Okay, so now try to compare this with the rectangular coordinate system. Remember, in our Cartesian coordinate or the rectangular coordinate system, if you specify the location of a given point, such as point R, you specify the location of point R in terms of the distances it makes with the x-axis and the y-axis. So its corresponding shadow projections on x gives you the x coordinate of that point, while the shadow projection of the same point on the y-axis gives you the y-coordinate of that point. Now, of course, the coordinates of a point is expressed in the ordered pair xy, and the sign of xy depends on uh, the pair of sign assignments from which the point is located according to the quadrants it would fall. Now, as compared to the polar coordinate system, instead of having an ordered pair xy as a pair that corresponds to the location or the projection of that point on the x-axis and the y-axis, we also make use of a pair, but this time in terms of distance from the origin, which is p as indicated here in this example, and the angle theta, which uh, the line segment which the point makes with the origin makes with the standard positioning of ray, which we normally take on as the x-axis in our Cartesian coordinates. So the assignment of the polar coordinates is represented as this pair p theta. Okay, so point O is called the origin or the pole, while ray H is called the polar axis. Okay, so in our Cartesian coordinate, the positive x-axis is considered as the polar axis, and the origin is considered as the pole. Okay, so let's try to present some examples or drawings that we can picture the polar coordinate system. Okay, so of course we are familiar with the rotation of the of our unit circle. So of course, the corresponding angles, the angles that are ray that will be made if you're going to rotate the ray around the circle, we can have multiples of, for example, of the special angles that uh, we were introduced during our trigonometry. So, for example, we have multiples of 30. So we have 30, 60, 90, 120. 150, 180, 210, 240, 270, 300, 330, and 360. We can also make this as multiples of 90. So we have 90, 180, 270, and 360. We can also make the rotation with multiples of 60. So 60, 120, 180, 240, 300, and 360. Okay, so if point W has a polar coordinate 3 and 60 degrees, then plotting it on the polar coordinate system would be like this one. If you're going to make use of a scale wherein one unit of the scale in our Cartesian coordinate in our coordinate system represents one measure, then the point W, which has three measures of that unit, would correspond to 3 units in our scale. So from here, we'll just simply make a ray from our pole, ending up with an arrow that ends up at the where the arrow tip would end up at the location of the 3 unit scale, and having to rotate the ray from our polar axis, ending the drawing of the ray 60 degrees from our polar axis. So we will be drawing the ray from our origin up to the point W. Okay. We can also draw a polar coordinate system as follows. So for example, instead of having a scale that is 1:1, one unit corresponds to one measure in a given scale, we could also make use of a different ratio for our scale. So for example, instead of having a 1 unit scale, 1:1 unit scale, we could use 1:2 is to 2. So for example, if we're going to use that scale, that means we will be having 2, 4, 6, 8, and so on as our scale measure in our polar coordinate system. Okay, so also we could instead of having, for example, multiples of 30 or multiples of 60 or multiples of 90, we could also make use of other different set of multiples such as multiples of 45 degrees. Now, of course, we all know the mentioned angles. These are called special angles in our trigonometry. Now the multiples of 45, of course, are the following: 45, 90. 135, 180, 225, 270, 315, and 360. Okay, so we can also draw the polar coordinate system as depending on your need, as long as the ratios between the measurements are preserved. We can also extend the polar coordinates to negative numbers considering the point Q, which is negative 30 and 60 degrees. Okay, so negative 30 and 60 degrees means that the measurement of the uh, negative 3 measure is measured on the negative x-axis, so that is 3 units. So if this length is 1 unit, that corresponds to 1 unit to the left. So negative 3 corresponds to negative 3 units to the left of our origin or our pole. So that means you will be ending the line segment or the ray at this point. Now, measuring 60 degrees, the 60 degree measure corresponds to to this angle here, ending up the point Q at this point, and forming the line segment OQ from our pole or from our origin. Now, notice if you're going to compare the two givens or the two examples, the first example is point W, which was measured as 3 and 60 degrees. The other example, which is point Q, is negative 3, 60 degrees. Notice that both of these two examples make use of 60 degrees, and 60 degrees is considered positive. And try to notice that the angle measurement for 60 degrees was measured in on both examples counterclockwise, in a counterclockwise sense. So that means this would give us a hint or a clue that whenever we measure angles and we do the measurement of the angles in a counterclockwise sense, it is always that the measure of that angle is in its positive sense. Now, also from these two examples, we can see that the sign of the magnitude of the uh, coordinate 3, positive 3 for W, negative 3 for Q, uh, the sign depends uh, the on which quadrant did we measure the that coordinate. So the positive sense of the measurement corresponds to a measure from the positive x-axis, while a negative sense of that measure corresponds to a measure of the coordinate from the negative x-axis. Okay. Okay, so next, we just deflect point W with respect to the pole to achieve Q. It is that would be quite obvious since obviously they make use of the same magnitude 3. The only difference is the sign, so that means we just flip the position of W to the other quadrant. So since W is located on the first quadrant, its image would be on the opposite quadrant, which is the third quadrant. So it follows if you have a point coordinate at, for example, at the second quadrant, if you're going to flip it, it would be the corresponding point would be located on the fourth quadrant, and so on. Okay, so consider point T, which is negative 3 and 60 degrees. Okay, so okay, so okay, so consider point T. Take note that the given here for point T should be negative 60 degrees. Okay, so this is a typographical error. So this should be written as 3 and negative 60 degrees. Okay. Okay, so again, this is 3 and 60 degrees. Okay, so just like what we have done in our previous two examples for W and Q, whenever we have a magnitude of, in its positive sense, it is always that the that coordinate is measured in from the positive x-axis, and positive angle is always measured counterclockwise. So that means if we're going to invert the sign of the coordinates, if we have a negative sense of the magnitude, that means that we measure the given coordinate from the negative x, and if we have a negative angle, that means we measure uh, the the angle in a clockwise sense. Okay, so that means this is actually wrong. This is actually supposed to be negative 3 and 60 degrees. Negative 3 following the described methodology for W and Q. Negative 3 should be measured from the negative x, so from here, positive 60. This means that we will be measuring the angle in a clockwise sense, in a counterclockwise sense. So this means that we'll be having that measure towards this direction, ending up at point Q. Notice that T is negative 3 and 60 degrees, which is the same as point Q. So, which proves that T here is actually is wrongly written in this courseware. So if the actual location of T is actually here, so this means that the corresponding coordinate for T should be positive 3 and negative 60 degrees. Okay, so I hope that you got the difference between um, the system of coordinates that we employ in order to locate points in our polar coordinates. Okay, so again, point T here is represented by the polar coordinate 3 and -60 degrees. Okay, so I will not be presenting to you these examples. I will be asking you to do these examples as your exercises, and I am expecting that you will be submitting this on before the final exams. Okay, so I'll be skipping the solution. Okay, so let's proceed now with the conversion of coordinates. Okay, so consider superimposing the rectangular coordinate system with the polar coordinate system in such a way that their origins meet. Okay, so just like what we have in our Cartesian coordinate, the Cartesian coordinate is represented by two lines. One is horizontal, representing our x axis, and one vertical line representing our y axis. And if we're going to superimpose the drawing of our polar coordinate system in our rectangular coordinate system, we will be seeing this kind of figure. Now, let us consider a point Q where polar coordinates are represented by r theta, where theta is a radian measure. Okay, so before we proceed, let us define first the radian measure. The radian measure is the measurement of an angle, which has a unit measurement equal to the ratio between the radius of the circle, which has 1 unit, divided by the arc of the that ray made which is the arc which is of the same length as the radius. Okay, so for to illustrate that, for example, this is your ray here. Okay, so for example, the length of this ray corresponds to the length of this arc. An arc, by the way, is the a line which the ray makes with the polar axis, and the distance of that from the tip of the ray from the polar axis in the curve line here represents the arc. Of course, the whole arc of the circle represents the circumference of the circle, so therefore a portion of an arc is actually a portion of the circumference of the circle. Now, if it happens that the radius of the circle and the arc length is of the same length, if you're going to take the ratio of the two, so that gives you one measure unit, and that one measure unit is actually equal to 1 radian. Approximately, if you're going to if you have, for example, a conversion calculator um, in your computer or in your calculators or in your cell phone, if you're going to look for a conversion between the radian measure for angles. Okay, so let me just. Okay, so let me just compute that. So this is 1 radian. Okay. Okay, so in terms of degrees, you could try to research on the value of 1 radian in terms of the degree measure. The degree measure of 1 radian, meaning that the ratio of the radius of the circle divided by the arc length, where the length of the radius is equal to the length of the arc. If they are equal, and if we're going to take the ratio that is defined as 1 radian, in terms of degree measure, 1 radian is equal to about 57.29578 degrees. Okay, so you could research this on your in Google, or you could try this in your calculator if you have a conversion factor or a conversion calculator in your scientific calculator. Okay, so let's consider point Q, where the polar coordinates of Q is represented by r theta, where theta is our radian measure. We therefore have the transmutation from the polar coordinate system to the rectangular coordinate system for point Q as follows. No? Okay, so from our origin to the location of point Q, the distance is represented by r, and the angle made by our ray OQ with our um, polar axis is given as theta, and that point there corresponds to the corresponding rectangular coordinates projection in x and in y. Okay, so let x and y be the rectangular coordinates of Q. Using the trigonometric function, we have x as equal to r cosine theta and y is equal to r sine theta. So how did we arrive with x equal to r cosine theta and y is equal to r sine theta? Now, of course, if we're going to draw the projections of Q on our x-axis and on our y-axis, we will be forming this sort of rectangle, and from there, that rectangle, we will be considering one of the triangles formed, where that triangle is actually a right triangle, and the right triangle there has the hypotenuse, which is the distance between OQ, which is our r, and our angle is within the our right triangle is our theta, and the sides of the corresponding right triangle corresponds to the distances or the projections of Q on our x-axis and on our y-axis. On that right triangle, the x-axis is actually the adjacent side, and the the x projection would be our um, adjacent side for our angle theta, and the projection on the y-axis would be our opposite side for our angle theta. So therefore, we can solve, or we can make use of trigonometric functions of sine and cosine to compute for the x component, or the x component and the y component. So obviously, since the x component is the adjacent side, we will be using cosine. Of course, cosine is defined as adjacent side, which is x, divided by the hypotenuse, which is r. Solving for x, that would be x equals r cosine theta. Now, the same goes for computing for y. Since y is the opposite side of our formed right triangle, we will be using sine to compute for the opposite side. So since sine is defined as sine theta is defined as equal to the opposite side y divided by the hypotenuse r. So solving for y, that would be equal to r sine theta. Now, through these equations, we can convert polar coordinates to their corresponding rectangular coordinates. To convert rectangular coordinates to polar coordinates, we make use of the definition for our inverse tangent or arctangent. Remember, tangent in our right triangle, tangent is defined as, or the tangent theta is defined as the opposite side over the adjacent side. So that would be y divided by x. So if we're going to take the arctangent to solve for theta, that would be arctangent theta y divided by x. Now, as for the hypotenuse, which is r, to solve for the hypotenuse given the sides of our right triangle, which is x and y, we can make use of the Pythagorean theorem in order to compute for our radius r. So that is why we have here r as equal to the square root of x squared plus y squared. Okay? Now, using the above solution or conversion from polar to rectangular, we could actually somehow modify the equation to have a direct conversion between the representation of x and y in terms of sine and cosine, and those with the presented equation for arctangent and the Pythagorean theorem r equal to square root of x squared plus y squared. So that is actually presented here. Now, since r is equal to the square root of x squared plus y squared, which is this one, and individually x and y is represented by x r cosine theta and y is r sine theta. We could actually replace x squared plus y squared by um, r cosine theta square plus r cosine theta square, and that becomes r square cosine square theta plus r square cosine square theta. R square is a common factor. If you're going to factor it out, that would be r square cosine square theta plus um, okay, so again, there is a typographical error here. Now, x square is r cosine theta square, while y square is actually r sine theta. Okay, so take note of the typographical error in this courseware. So this is supposed to be r cosine theta square plus r sine theta square. Okay, so this is not cosine, this is sine. Okay, so replacing cosine with sine here, this becomes sine square, and still this is cosine square. Factoring out r square, this becomes cosine square theta plus sine square theta. Okay, now what is sine square theta plus cosine square theta? Now, for a unit circle, that means if you're going to have the radian measure of r equal where the radius of the circle is equal to 1, so that means if you're going to have cosine square theta plus sine square theta, that is actually um, equal to your the definition of the trigonometric identity from your trigonometry. That is one of the basic Pythagorean identities. Cosine square theta plus sine square theta is equal to 1. So that means this is 1. So that is why you can no longer see here this expression in this factor. So what is left here is x squared plus y squared is equal to r squared, which brings us back to our original expression for r if we're going to get the square root. So r is equal to square root of x squared plus y squared. So since this would be the proof for our representation for r. Okay, so in this example, convert the polar coordinates in example 1 to rectangular coordinates. Okay, so x is equal to r cosine theta, y is equal to r sine theta, and x is given as 3, and cosine theta is 225, 225. Okay, so you could try computing using your calculators for cosine 225, or you could actually look at your trigonometry notes so that you can express the given value for cosine 225 in its exact form. So doing that, notice above that the angle 225 is actually a multiple of 45. So going back to our polar coordinate system, 225 is a multiple of 45. So therefore, its corresponding x and y value for its cosine and sine is the same as those of the 45-degree angle. And remember in your trigonometry that the cosine of 45 degrees is equal to square root of 2 over 2, and its sine 45 is also equal to square root of 2 over 2. Therefore, if you are going to find cosine 225 and sine 225, the corresponding values for cosine and sine are also 220 square root of 2 over 2, but we will be giving them signs depending on which quadrant the angle is located. So since 225 is located on the third quadrant, and on the third quadrant the x-axis is negative and the y-axis is also negative, so therefore if you're going to compute for cosine 225, that means cosine 225 is negative square root of 2 over 2 times 3, so that gives us negative 3 square root of 2 over 2, while r sine theta gives us sine 225 is also negative square root of 2 over 2 times 3 gives us negative 3 square root of 2 over 2. Okay? Now, number two. So we have r cosine theta, where r is equal to 1 and theta is equal to negative 30. Now, remember our convention for determining the location of an angle that is negative. An angle, negative angle is measured from the positive x if the magnitude of r is positive, and it is measured clockwise from the polar axis. So this means that r cosine theta, or 1 cosine negative 30, is actually located on the fourth quadrant. And on the fourth quadrant, x is positive and y is negative. Okay, so let's compute for cosine negative 30. Negative 30, if we're going back to our, if we go back to our polar coordinate, of course, negative 30 corresponds to the location of the ray that which coincides with the angle 330 degrees. Okay, so since the angle is measured negative 30 and the value of r is positive, so that means the angle it was measured in the positive polar coordinate, or the polar axis, or on the positive x, measured clockwise in the clockwise sense. So this means that the angle will be, the ray will be located here on the fourth quadrant. Now, notice if the ray is located here, and if we're going to form our right triangle has the shorter leg on the on the y-axis and the longer leg on the x-axis. So therefore, if we're going to get or compute for the value of sine and cosine in its exact form, remember in your trigonometry that cosine 30 degrees is equal to square root of 3 over 2, while sine 30 degrees is equal to 1/2. Now, since cosine negative 30 is located on the fourth quadrant, and on the fourth quadrant, the sign of x is positive. So therefore, if you're going to compute for cosine negative 30, that would be a positive square root of 3 over 2. X, remember, x corresponds to the longer leg of our right triangle. Okay? Now, while r, which is r sine theta, which is y, on the fourth quadrant, the sign of y is negative, so we expect that the result for r sine theta is equal to a negative value, just like what we see here. And the projection on the y-axis of our right triangle, considering that the angle is negative 30, is the shorter leg. So between square root of 3 over 2 and 1/2, 1/2 is actually the shorter measure between these two. So this means sine negative 30 is equal to negative 1/2. Okay, so I'll be leaving example number 3 and example number 4, also 5 and so on, to your own verification. Okay, so also I'll be asking you to do this example number 3 as an exercise. Convert the following rectangular coordinates to polar coordinates. Okay. Okay, so I'll be cutting this video lecture at the moment. I'll be continuing with the next video lecture. Try to answer, remember, try to answer the exercises that were presented in this video lecture.